portion of the discussion. Okay, so B was, man, now it's going to start lagging probably. E to the minus log 4 quantity squared. Okay, so of course log is the natural log. So when you see this, what does your brain want to do?
I believe that we can, well, basically do as the squared says and basically take this and make it e to the power of, I believe it would be -2 log base 10 of 4.
Negative, oh, so this is log base e, right? So natural log.
Oh, right, okay, because
Yeah, from
yeah.
now on, all logs are log base e's. Okay, yeah, so I agree power to a power means multiply, so that's fine. Minus 2 log of 4, good. Alright, now what? So if this were e to the log of something, it would be very easy to cancel, right? Because e and natural log are inverse operations. So it would be nice if we could use log of a power backwards to get this inside and then be able to cancel. So if I wanted to use log of a power backwards, what would the argument, the inside of the logarithm become?
So the inside of that logarithm would become 4 to the power of -2 or 1/16.
Yeah, so e to the log 1/16. Good. And then the trivial final step, what is this?
I believe this would just be 1/16.
Very nice. Good.
Whoa.
Yeah, not bad. Okay, so it seemed like you knew what was going on. It was just this step that might have not been obvious initially. Good, good. Other questions on this?
I have no questions. I guess I should have looked at this further before I got confused with it and said W, work in progress.
Whip!
With spells with no H.
You said B specifically, so you're not interested in C and D?
I don't believe I understand C, but I might and just not realize it.
Alright, let's just
I
bang it
guess.
out. It'll be faster, so...
Oh wait, would this just be log? I believe this would just be log 7 over log 3, right?
Yeah, exactly. Log base 3 of 7. The change of base formula just says that the natural log, this is like log base a of b and log base a of x and log base a of b, right? So log of 7 over log of 3 is precisely right. Good.
Okay, that's cool.
Why are we getting messages? Shut up. Sorry. That sounded meaner than I wanted it to. Okay, should we talk about D? This is related to Jason's objections about defining your own variables.
Sure, why not?
I mean, unless this one seems boring to you, but I think it's kind of cute, actually.
I don't understand it, so sure.
Oh, okay, good. I wasn't sure if you were hesitating because it was too easy or not clear enough. It's always hard to tell. 3e to the x minus 4. So I've made a comment about this earlier today because we were talking about supersymmetry, and I haven't worked a lot with supersymmetry, and he wasn't sure what parts to explain to me, and then I told him the thing that he said that I didn't know, and then he just looked off in the distance for a second, and he's like, wow, it's like explaining to someone how to add. Like, it's been so long since I didn't know how to add, I don't even know how to explain how to add. Okay. Sorry. This is not like that. I just thought that was funny. So the scaffold here was to use my favorite trick and define a new variable, y equals e to the x. Okay, so my question to you is, if we define y equals e to the x and then replace all occurrences of e to the x in the original equation by y, what equation do I get in terms of y?
That would be y to the power of 2 minus 3y minus 4 equals 0.
Good. Now, since you've had the, I mean, I'm sure you've factored quadratics ad infinitum in this forced babysitting course, so what should I write to factor this bad boy?
That would be y minus 4 times y plus 1.
Good. Y minus 4, y plus 1. So now we have to be careful, and this is probably not something that was emphasized in your algebra class, but whenever you solve a quadratic that came from a different problem, like if you're given a word problem involving areas or something and you convert it to a quadratic and then you solve it, you should always check whether one of the roots is spurious, which means it doesn't actually solve the original problem. Because in solving a quadratic, you'll sometimes introduce a fake root. So I'm going to replace, using the original definition, y equals e to the x. E to the x equals 4, so I'm just rewriting the solution for y in terms of e to the x, and e to the x equals minus 1. So are both of these solutions valid, or is one of them spurious?
I don't believe that e to the x can equal -1.
Good, yes, this cannot exist. We've defined exponential functions. One of the properties is they only output positive values. So that one is indeed spurious. This one we can solve. So since we're asked to solve in terms of x, what is this? I mean, you can just take the log of both sides. What should I write the solution for x as?
I believe that you can write log 4 equals x.
Yeah, log 4. Okay, so the only trick, well, there were two tricks. The one trick was defining a new variable. The second trick was double checking to make sure both of your solutions are, or checking that checking each of your solutions for spuriousness and finding one of them is spurious. But yes, this is the only real solution, x equals log 4. Good. Does that make more sense now, or is it still confusing?
This makes sense as much as it did before. This is cool.
Wait, as much as it did before, but you said it didn't before.
Whoops.
I wasn't sure if that was accidental or if you're still confused.
Like, as soon as I spend more than 10 seconds on all the problems for 6.3, it started making sense. So I guess I should have just put more time into it.
That's fine. I mean, I don't mind talking through them, so you don't need to put more time into it necessarily. But okay, so I think we're caught up on these. Was there problems here? Yeah, okay. So these challenges, it's probably harder to go through because in 6.5 I just asked you to pick 3 of the definitions from this list of learning goals and write precise definitions, where I gave examples of good meaning precise and bad meaning imprecise. So maybe that one's easier to do on your own. This one, yeah, I've also asked you to just look back at a daily challenge you couldn't solve and to rewrite a solution. So I don't know, do you want to go through that? If you have one in mind, we can work through the solution now, or do you think it's better to skip that one for the meeting?
I believe we can skip this one.
Okay. Good. This one, yeah, this is not very involved. This is just a short video on reviewing philosophically what we've done and previewing chapter 2, and then I ask you some qualitative questions about explaining a limit as you understand it now, what is a pathology, which is explained in the video, and a feedback question about what's useful. And then
Quick question. By useful, do you mean that we've applied most in this class, or seen used the most in our other classes and / our real life?
I mean useful as in whichever is most aligned with what your goals for the group are. So if it's the first of those, if you're doing this calculus group mostly because you want applications to other classes, the first one. If you're interested mostly in applications to real life, the second one. It's whatever, it's based on your preferences.
I'm doing this mostly because it's fun.
Okay, good. I mean, that's why I'm doing it as well. So then, in that case, the question becomes, which of the things we've discussed have you found the most fun? Okay. Then, I think... What's that? Yeah, this daily challenge was rewriting a thing from P set 1 about Suprema, and then this daily challenge was... No, not that one. This one. This was rewriting the solution about showing that a strictly increasing function passes the horizontal line test. So do you want to talk about either of those, the horizontal line test one or the Suprema one?
Wait, is that my sentence there? The function f passes the horizontal line test because it would solve for every x value. Yeah, that thing.
Yeah, that was... I called it the original response, but I meant your original response.
Oh, yeah. I don't know why I said that.
Well, I phrased it. I mean, it's a legitimate question because I said the instead of your, but for some reason when people use your, I find it somewhat accusatory. Like, oh, your. This is your opinion. I don't know. So that's why I said the instead of your.
I said, I don't know why I said that because I said, oh, yeah.
Wait, you don't know why you said oh yeah because you realized that it was yours? Or what?
I have no idea anymore.
It was a confusing sentence. Okay. Do you want me to walk through this proof, or do you want to read through this stuff on your own and give it a try? Whatever. I guess we should do whichever daily challenge you think it will take you the most time to do, because you probably want to optimize for finishing them, right?
I don't know which of these will take me the most time. It doesn't seem like any of them would be hour-long challenges, as far as I can tell.
Yeah, they're mostly just revisions, so I don't know. I guess it's up to you. So if you want, I can help you revise any of these by like walking through what I think it should look like, or if you want to talk about something else, we could do that. I don't know. It's your preference.
Doing the Blitz questions now would be cool.
Ah, those things. Okay. Good. I like blitzes because I like fast. What, just for feedback, was the pace of questions when it felt like we were going at the right pace in the last meeting while I was in the moment. I think that was just because during flow, your sense of time is distorted. When I watched the video afterwards, it felt a little slow from the observer's perspective. So was the speed of answering questions last time just right, too fast, or too slow for you?
I don't know. I think it felt right.
Okay. Well, if I'm going too fast, just interrupt me and tell me to stifu. But okay. All right. So this is some more review on inverse trig stuff. So if we composed, so by the way, I mean maybe a better way to write this, not better, but just to make sure you understand composition notation, is it clear that this is the same as writing cosine circ arcsine of x? Is that clear what that notation means?
I have never seen that before, but I understand now.
Okay, good. Yeah. In general, so another example, if f, maybe I should do this somewhere else. If, just a quick check. So if f of x is e to the x and g of x equals, I don't know, tangent of x, then what is f circ g, or f composed with g, or fog? What is fog of x?
I believe that would be tangent of e to the x.
Ah, careful. That's g composed
Oh wait,
with
no,
f.
that's the wrong way around. I don't. What? I was seriously thinking deeply about the order for some reason, and I still answered it wrong. What is
So what you said was this one. You said tan of e
e
to
to
the x.
the power of tan x?
Good. Okay.
That wasn't right. E to the power of tan e. Wait, what? No. Ah! Suffering.
I feel like that was just a silly mistake, though. You see what we did, right? We just took tangent and put tangent of x where x appeared in the first one, right?
Yeah.
Okay, good. Okay, so now we know what composition means. It's back to this thing. So if we compose cosine with arcsine, this looks a little weird. Like if we composed cosine with our cosine, It's for most values, that's the inverse function. Here is cosine and arc sine, which looks a little trickier. So do you have any ideas about how we could simplify this and write it in a way that has no trig functions?
Well, we can start by figuring out what arc sine is.
Oh, well, you know this. This is sine inverse, right? Arc sine is another way of writing sine inverse of x.
Oh, right.
Yeah. Good. Maybe one way to think about it, do you remember any identities? If we could write this cosine in terms of sines instead, then it would be easier to simplify because we know how sine and sine inverse interact. So do you remember any identity that lets us trade a cosine for a sine?
I believe that. I guess a substitute, since I'm gonna start using improper wording, a substitute for cosine would be sine like shifted pi.
Oh, good.
I don't know.
That's interesting. Yeah, does that help us? So you're saying cosine of theta plus pi over 2 is going to look like sine of theta. So, interesting. Does that help us? Well, so if we replace this with, so you're saying we could replace the cosine with sine. I'm going to write sine inverse instead of arc sine because I feel like you like that notation better. Sine plus pi over 2. So I agree that works.
That's exactly what I meant.
This is what you meant?
Yeah.
Okay. I agree that this is equal. How do we simplify this now? This is sine a plus b. Actually, yeah, this is not how I thought how to do the problem, but you could do it this way, I think. Because this is, remember, sine a plus b. Remember this formula, sine alpha plus beta is sine alpha cos beta plus sine beta cos alpha. So, oh, we're stuck though, right? Because if you use this formula, alpha is sine inverse of x, beta is pi over 2. So the second term, when we put in sine beta cos alpha, sine beta is 1, and cos alpha is cos sine inverse of x. So if we try to do the problem this way, this term becomes cos of sine inverse of x.
It is interesting.
Yeah, and that's back to where we started. Man, I thought that was going to work for a second. That was interesting. Okay, so sorry, that one took us in a circle. That was good. And I admire your creativity, though. I did not think of that. What about sine squared theta plus cos squared theta is 1. What happens if I solve this equation for cosine?
I believe in this case it would be. Trying to remember how to word this. Okay, this is going to be a very dumb question, but I can't remember. Is sine squared theta sine theta squared?
Yeah, this is confusing notation. Sine squared theta means sine theta quantity squared. Yeah.
Okay, I believe that we can define cos of theta as 1 over, the root. Okay, huge root fraction 1 over sine of theta.
1 over. This is a plus here, right? So we're not. I think you divided both sides by sine theta.
Oh.
Yeah.
Amazing job, Zelf. So that would just be 1 minus sine squared theta?
Yeah, good. So we just pop this over to the other side with a minus sign, take a square root. good. So,
Imaginary numbers soon.
well, I don't think we need imaginary numbers. Technically, this would be plus or minus, but let's suppose we're in the quadrant where cosine's positive. Now, how does this help us? Well, then I'm just going to rewrite what we had in terms of sine. So the original thing we wanted to compute was cosine of sine inverse of x. And now we know for any theta, cosine of theta is the same as square root of 1 minus sine squared theta. So in particular, we could just let theta be this whole thing inside. Theta is sine inverse of x. So that means this is square root of 1 minus sine squared. Now what is theta? Theta is sine inverse of x. Aha. Alright, so is it always true? This is actually a concept question about inverse questions. Is it always true that sine of sine inverse of x is equal to x?
I don't believe so.
Do you have a counterexample for where this is not true?
Well, one possible example would be where x is not defined for the inverse of sine. So, for example, wait, let me think. I don't believe that the inverse of sine is defined for 2 pi, so sure, that'll work.
Yeah, 2 pi is outside of the range, right? Or outside of the range of sine, which is the domain of sine inverse. So I agree. What if we assumed, as in the question, so the question says assume that x is between minus 1 and 1. So now,
Okay.
if we make that assumption, is it always true that sine of sine inverse equals x?
Yes.
Good, okay. Let me ask one more question. Is it all, again assume x is between minus 1 and 1? What if I flip the order? Is it always true that sine inverse of sine x equals x? Just careful. We saw these things about inverse. I mean, this is not an image. This is just the function. But we saw that there was some really tricky shit going on if you reverse the order of inverses and regular functions, right? So I agree the first one on the bottom, this is always true. But can you either prove or disprove the first line that sine inverse of sine x is always x?
I believe that it is still a valid, well, is valid the correct word? Just that statement is, equation is valid.
Okay, good. So we should talk about the domain of sine inverse, because remember, by the way, it's like, what is it, 9 o'clock for you? When do you have to leave?
Preferably before 10.
Okay, good. I'll try to be brief then. So, all right, let me go wait to the. This is important. This is one of the things on the learning goals that I have to make sure you understand well. So, remember when we wanted to invert the graph of sine, because sine is not 1-to-1. It fails the horizontal line test, right? So sine goes like this, and then like this. So we said sine cannot be inverted because it fails the horizontal line test, right? There's multiple outputs that are achieved for, or sorry, the same output is achieved for multiple inputs. So what did we do? We said we're going to restrict the range of sine. We're going to chop it so it's between minus pi over 2 and pi over 2. This was in the daily challenge about the inverse sine and inverse cosine. And then we said if we chop it so that it's between these guys, now it passes the horizontal line test, and we could define an inverse function on this restricted domain. So then we decided that the range of the inverse function, range of sine inverse, or sorry, domain. well, I'll write the range anyway, but I was really interested in the domain. So the range of the sine inverse, which is the domain of this restricted sine, is minus pi over 2 to pi over 2. And that means the domain of sine inverse, which is the range of this restricted sine, is minus 1 to 1. So this is important, because if the range of sine inverse is minus pi over 2 to pi over 2, that means sine inverse always outputs a number which is between minus pi over 2 and pi over 2. So in particular, if I ask, I don't know, what is sine inverse of sine of pi? Let's just work this out. So what's the inside part of the brackets? So what is sine of pi?
Sine of pi would be 1.
Let's see, so pi is 180 degrees, right? So that's over here.
Wait, oh. Oh my god.
So what's that?
That would be 0.
Good. Now what's sine inverse of 0? And remember, sine inverse always outputs a number between minus pi over 2 and pi over 2. So what value in that range gives me a sine of 0?
I believe 0 again.
Yeah. So sine inverse of sine pi equals 0. So is it always true that sine inverse of sine x is necessarily, I'll put a question mark, is this always going to be x?
I do believe so.
Well, how can this be true? Because the line before, just let x equal pi. In this line, sine inverse of sine of pi is 0. So if the second line were true, it would have to be true letting x equal pi. It would have to be true that...
Oh, I see now.
See what I'm saying? We would have to have sine inverse of
Because
sine pi.
sine is periodic, and that means that the final... Yeah, that's cool.
Okay, good. So you now agree that sine inverse of sine x is not always x, because here's an example where x is pi, but sine inverse of sine x is 0, and 0 is not the same as pi, right? Is that clear, or should I go through it again?
I do understand.
Okay, good. Okay, so this is very important. So we should recognize that the first form, the way I wrote it where sine came first and sine inverse came second, that one's always true. The second way I wrote it where the sine inverse came first is not always true, right? So just going back here, we found out that this is false. The counterexample was pi, which you gave. So this is false. And my pen's broken. This is false and this is true. Okay, good. So now that we're happy with that, which of those two cases happens here? Well, remember sine squared means sine of the quantity squared. So this is the same as sine of sine inverse x quantity squared. So what does that simplify to on the next line? Or would it help if I wrote it out without sine squared, if I wrote it out explicitly?
I believe that would help, possibly.
Okay.
I'm not seeing a easy way to simplify this.
Okay, what if I make a larger square root, and I'm just going to replace sine squared with sine of the quantity squared, so I'll use brackets. 1 minus sine of sine inverse of x quantity squared. Okay, do you see how to simplify that now? Perhaps we should go back up here and remind ourselves of which one of these is true. So remember, sine inverse of sine x is not always x, but sine.
Oh, but we can simply set it to x.
Yeah. So this becomes what, 1 minus x squared, right? I didn't need that big square root. Shit.
I'm over here dying.
Okay. I mean, yeah, I realized that was a tricky question because of I injected all of the intermediate questions. But is it clear what we've done so far? We just took cosine of sine inverse, replaced the cosine by Pythagoras, and then we checked that this thing is always x. Are you happy with the procedure at least?
Yes. Also, I like the phrase by Pythagoras because it sounds like by Merlin's beard or something.
I always, instead of quoting theorems, I like to speak about the mathematician who proved the theorem as though he's personally helping me. Like, by Euler, we got this. Like, okay. Good. Okay, so this is square root of 1 minus x squared. There's a picture that helps me remember this. The picture is not a proof. The picture is a mnemonic. But it's often useful to think about how these trig of inverse trig functions are going to work. So I'm just going to draw a triangle. We're interested in cosine of sine inverse of x. So we want to pick an angle whose sine is x. So I'm just going to choose that to be the angle in the lower left here. So this angle, say, is theta, and we want sine of theta to be x, since we're talking about something that involves sine inverse of x. So if sine theta is x, I can choose the sides of this triangle to be whatever I want as long as sine theta equals x. And sine theta is opposite over hypotenuse, so I'm going to choose the height of this to be x, and the hypotenuse to be 1, because then sine theta is x over 1, which is x. Okay, so suppose I do that. Now what is the length of this bottom side, the horizontal length? What is this?
Wait, let me think. So that would be, give me a sec to think about this.
Cool.
That would be cosine of theta equals, I'm just going to define that bottom side as y.
This is y, okay. Can you give me y in terms of x using the Pythagorean theorem?
By the Pythagorean theorem, okay, I think.
Well, let's do it I mean, I want to
wait.
always. Let's do short steps. What is the Pythagorean theorem if this is y? What is the relationship?
X squared plus y squared equals 1.
Okay, and if I solve that for y, what is y equal to?
I believe that y is equal to the square root of 1 minus x. I guess I omit the plus or minus. Can I? No.
Let's assume these are positive because they're lengths of a triangle, so you can omit the plus or minus.
Right.
Square root 1 minus x squared, right? Because this term is x squared.
Right.
Good, okay. So I changed colors by accident. Okay, so y is square root of 1 minus x squared. Good.
Oh no, I'm black.
Oh no, now racism happened. Okay, so what's cosine of theta then? Cosine of theta is adjacent over hypotenuse. Adjacent is y. Hypotenuse is 1. So cosine theta is y over 1, which is y. And you've just told me y is the square root of 1 minus x squared. So do you agree that in this triangle I've drawn, cosine theta is square root of 1 minus x squared?
Yes.
Okay, here's the kicker. So we pick this whole triangle, so sine theta equals x, which means up to some questions about where the angle lies, which we'll ignore because we've drawn the triangle to be acute. Theta is sine inverse of x. So if I plug in theta equals sine inverse of x into that expression for cosine of theta, then cosine of what? Cosine of theta. What is theta? Theta is sine inverse of x, so this should be cosine of sine inverse x is square root 1 minus x squared. And lo and behold, that's exactly the same expression we got by doing this thing with the trig substitution, right? This whole procedure we did up here, using Pythagoras, told us that cosine of sine inverse of x is square root of 1 minus x squared. So you can think about this result either by using the Pythagorean identity for trig functions, substituting in and canceling, or inverting, I guess, and getting this, or you can think of it as drawing a triangle, choosing an angle so that sine theta equals x, and then asking, okay, now what is cosine of theta? Cosine of theta then is square root 1 minus x squared. Two ways to see the same result. Okay, questions on this?
I have no questions. It's still really cool. You mind if I take like a 30-second break to get a water bottle?
Yeah, sure. I will be here. Okay, good. Back to business. Okay, so you may remember last time we had the formulas for hyperbolic trig functions, right? So cosh of alpha we wrote as e to the alpha plus e to the minus alpha over 2. And that's a bad fraction bar. Over 2. Sinh alpha was the difference, e to the alpha minus e to the minus alpha. So I told you this nice story about how these label points on a hyperbola, but you might have asked the question, okay, I know what hyperbolas look like, and I know they look like the equation x squared minus y squared equals 1, but where did these e's come from? Why does the number e have anything to do with a hyperbola whose equation is x squared minus y squared equals 1? This equation has no e's in sight. I don't understand why e's are needed to label points on that hyperbola. That's a very reasonable question. I realize I should probably answer that question. So we're going to see why these formulas are very natural if you think of Euler's formula for the regular sine and cosine. So let's do that first. I'll ask you, tell me what Euler's formula gives for the two expressions e to the I theta and e to the minus I theta. What are these equal to?
We've done this before. I'm doing some Googling of sorts.
Actual Googling or Googling through your head?
Yes.
Both. Okay. All right, I'll give you the first one. But this is something that this has to be in your cache. I mean, you don't have to memorize it. You can figure out what it has to be just by thinking about some examples if you want, but it should be something you can work out pretty quickly. So
yeah, this is the thing I should have memorized. The Euler's formula for the... Okay, there are... Oh, wait, I see how this is, but you can do your thing.
I don't understand that comment.
The upper orange equation, I remember this.
Ah, you remember this now. Okay, so maybe you can tell me the lower orange equation, e to the minus I theta, and simplify as much as possible. What is e to minus I theta going to be?
Could it possibly be as simple as the entire upper equation? Wait. 1 over the entire upper equation? Or is that too simple?
It is. Oh, okay. Wow. Okay. Yeah, let's do it that way. That's interesting. Yeah. That works, actually. Man, you're full of interesting insights. This is going to give us the same answer as the thing I was just going to do. 1 over cos theta plus I sine theta. Now, let's simplify this by multiplying by 1. Remember, our two tools are adding 0 and multiplying by 1. So I'm going to multiply by 1 in the following form. And it's just going to be the complex conjugate. So cos theta minus I sine theta divided by the same thing, cos theta minus I sine theta. Do you agree that the second expression I've written as a multiplicative factor is exactly equal to 1?
Yes.
Okay. If I multiply by that, in the numerator, I get cos theta minus I sine theta. Since that's easy, all I did was multiply by 1. What do I get in the denominator when I multiply these two things by each other?
I believe that you would get cos squared theta minus, oh, actually no, plus sine squared theta.
Interesting. That's another nice number. What number is that?
I think that's 1.
Yeah. So the denominator
Wait, these two are identical. Wait, no, they're not.
minus
Is
sine.
it?
Minus sine. Careful.
No.
Minus I sine theta. Good. So they're
Right.
almost the same up to a plus sign. The reason I was interested in the way that you did this is because I thought what you were going to do is say, oh, this formula is the same as the first one if I change the angle to be negative. So I thought you were going to copy this formula and say, oh, that's cosine of minus theta plus I sine of minus theta. And then you would remember, oh, but cosine of minus theta, by that mirror symmetry, cosine of minus theta is cosine theta, and sine of minus theta is minus sine theta. So we would get the same thing. But you did it in a way which required no trig identities. You just used the power to a power sort of thing, right? That this is 1 over that. So it's actually very interesting. Either way works. Okay, so let's add them, right? Because the nice thing about this is the top one is thing plus other thing, and the bottom one is thing minus other thing. So if we add them, well, I'll just write it a little more carefully because that sounded very sloppy. Have you solved in your algebra class like systems of linear equations where you have to eliminate a variable?
Don't quite know what you mean by the eliminated variable part, but we have solved linear equations before. Plenty of time.
But systems, like two linear equations at the same time?
Yes.
Okay. Okay, so you've probably seen something like this. So what happens when I add these two equations? What do I get?
In this case, you'd get 2 cosine theta.
Good. So add them, and I get, what's on the left side, though?
That would be e to the power of I theta plus e to the power of negative I theta.
Good. Left side is e to the I theta plus e to the minus I theta. Right side is 2 cosine theta. I'm going to divide by 2, and we get a formula for cosine. Cosine theta is going to be a half, because I divided by 2. It'll be e to the I theta plus e to the minus I theta over 2. And I'll spare you the torture of the algebra, but you can probably see that if we subtracted the two equations, if we subtracted the first one from the second, now it looks slightly different because now the cosines cancel and we get 2I sine theta, and then you can divide by 2I. So you get a different formula. Sine theta equals e to the I theta, theta minus e to the minus I theta over 2. So you agree we could do this and solve for sine and cosine. Are you happy with that system of equations?
Where did we lose the I in the lower purple equation?
I'm an idiot. That's what. Sorry, I made a mistake. Good catch. Thank you. Very good. Very good. You're keeping me honest. Okay. Now that it's correct, are there other questions about this?
I have no questions. This is still cool.
What does this look like? This looks very similar to something we saw a moment ago. Cosh alpha is e to the alpha plus e to the minus alpha over 2. Cos, with no h, of theta is e to the I theta plus e to the minus I theta over 2. The only difference between these formulas is what?
It would be the alpha being replaced with a I theta and vice versa.
Yeah, so the alpha appears in the exponential as a real number. Theta appears in the exponential as an imaginary number. So now I'll ask you a very interesting question. What is the cosine of an imaginary angle? What if I say I want to define a cosine of an imaginary angle, I theta, and I'm just going to, I don't even know what an imaginary angle means, so I'm just going to define it so that it still satisfies this equation. I'm just going to assume this is still true. I can plug in an imaginary value of theta. If I make that assumption, I'll pull out the half for you. What should I write in the parentheses if I'm replacing theta by I theta here?
I believe that this would be e to the power, wait, e to the power of negative, excuse me, yeah, negative theta, right? Yeah, totally.
Yeah, I swear it's -1, right? Second one.
And this one would be e to the power of theta.
E to the theta, okay. This is interesting because, I mean, if I just change theta to alpha, this is the same as the definition of cosh. So if just replace alpha by theta, cosh of theta is e to the theta plus e to the minus theta over 2. So that's the same as switching the order, e to the minus theta plus e to the theta over 2. So this is simply cosh of theta. So now there's an interesting relationship. Well, let me just spare you the details. You could do the same thing with the sine. You could see that if I plug in sine of I theta, now we're going to get e to the minus theta minus e to the plus theta, and there's still this factor of I. So I think this should be minus I sinh of minus theta. So up to some signs, but sine is in plus or minus, not as in the sine function. But anyway, the plus or minus and factor of I isn't important. What we've found now is that this very strange formula that we started with for cosh and sinh, which had e's, e to the plus alpha, e to the minus alpha over 2, that thing can be interpreted very naturally in terms of Euler's formula for cosine and sine, because solving for cosine and sine gives us very similar looking formulas except with i's upstairs. And the nice thing about this is now we have new relationships that define cosine and sine of imaginary angles. So if you ever wanted to take the cosine of an imaginary angle, we now see that that's the same as taking the hyperbolic cosine of the corresponding real angle. Or said differently, the way the interesting insight you pointed out last week was that a hyperbola is like a circle where one of the directions is imaginary, right? You said it looks like y is imaginary because we have a minus sign. So now we see a different way to interpret this. Instead of thinking of the direction as being imaginary, we could think of a hyperbola as something where the angle is imaginary, right? Theta is I alpha. Just plugging in an imaginary angle gave us a hyperbolic cosine. Okay, so I just wanted to make that connection a little clearer. What do you think? What is on your mind about this?
I say this is more words.
Wait, sorry, the audio glitched. I heard I say this is more words.
I say the phrase "this is cool" more often probably than I should.
Can you I'm not trying to attack you or like ask or be nosy about explanation. I'm trying to determine which features are cool so I can do more of those. So can you unpack what about this is cool to use so I can do more of it?
Just the entire thing.
Okay. All right, I think you have good mathematical taste. I think this is, well, okay. I mean, that's an arrogant statement because I think this is cool, so I'm assuming you have good taste because I like it. Okay, I'll just try to pick more things that I think is fun.
You're not helping your case.
Yeah, I'm just going to stop talking now. Okay, let's do some quick practice with suprema and infima. So let's see. Remember, supremum is the lowest upper bound, so you think about the space of all upper bounds and take the smallest. The infimum, you think of the space of all lower bounds and take the largest. So for each of these sets, we want to think about, does the supremum and infimum exist? If so, what is it? So first, this set of all the 1 over n's, where n is in n. And remember, my convention for n, other people sometimes include 0. But for me, this is the positive integers. 1, 2, 3, blah, blah, blah. So this is the set of 1 over 1, which is 1, 1 over 2, which is a half, 1 over 3, which is a third, 1 over 4, which is a quarter, and it gets smaller and smaller. So what do you think, what is the, maybe I should give this set a name. This set is A. So what do you think the supremum of A is?
I believe that the supremum of A, assuming that the natural number set would quote unquote include infinity, would be 0.
Would be 0. Well, so remember, supremum is the
Right.
upper bound, right? So supremum, that should be bigger than every element in this set, right? And this set includes like 1, a half, and third and stuff.
Yeah, I got suprema and infima confused, so this would be 1. Wait, no, would it?
What do you think?
I think it would be 1.00 dot dot dot. And then a 1.
Is there any real number that is infinitesimally above 1? Like, is the number 1.00 infinitely many zeros and 1? Does that number exist, and is it different from 1?
This got philosophical.
No, it's not. I mean, philosophical is a very dirty word in my opinion. This isn't philosophical. This has an answer. I mean, this is the same. Let me ask an easier question. What is 0.9 repeating? What number is that?
I guess the only answer is itself.
No, bad answer. Let me prove. You probably haven't seen this proof. Let's set 0.9 repeating. Let me do this in a different slide. This is very important, actually. This has to do with the structure of the real numbers, so you should definitely be aware of this. 0.9 repeating is another name for a number that we already know. I'm going to set a variable, I'm going to define a variable x for 0.9 repeating. I'm going to multiply both sides of this equation by 10. On the right side, I get 10x. On the left side, multiplication by 10 shifts the decimal point once to the right, right? So do you agree if I multiply 0.9 repeating by 10, I get 9.9 repeating, right? Because I shift the decimal place. Are you happy with that step?
Yes.
Okay. Now I'm going to subtract the first equation, call this equation 1, call this equation 2. Now I'm going to subtract equation 1 from equation 2. So I'm going to put a minus sign to help us remember. So
I see where this is going and I love it.
good. So minus 0.9 repeating and minus x. So when I subtract 0.9 repeating, what do I get on the left side?
I believe 9.
9, because the repeating cancel. What do I get on the right side?
9x, 9x.
9x. X equals 1. This is not a trick. Sometimes you see on Facebook or whatever these fake proofs that 1 equals 2 or something. This is not fake. The number 0.9 repeating, often if you ask people where is that on a number line, they will say something strange, like 0.9 repeating is very, very close to 1, but just a little less. It's not quite equal to 1. That statement is
But you can get closer.
Yeah, I mean, how could there be a number that is really close to 1 such that there's no number between that number and 1, but not equal to 1? We've proven in chapter 1 of AOPS that the real numbers have the completeness property, so there's no holes. The rationals have holes. The reals don't have holes. If 0.9 repeating were not equal to 1, there would be a hole in the real numbers between 0.9 repeating and 1. That is unacceptable. We cannot do calculus in a number system with holes. So the only possibility is that 0.9 repeating is exactly equal to 1. Not close, exactly equal to 1. And we've proven that here by a simple algebraic argument, just by multiplying by 10, right? So have you seen this, or did you know this before, that 0.9 repeating is 1?
No, but this is... I don't know how to feel about this. I love it.
Often people feel uncomfortable when they first see this, like they want to fight against it. So if there is any residual doubt or discomfort in your mind, here's another proof. Ready? What's 1/3 in decimal?
That would be 0.3 repeating.
What happens if I multiply both sides of this equation by 3?
It would be 1.
1, what's on the right side?
I guess 0.9 repeating.
Yeah, I multiplied by 3. 3 times 3 is 9, and it repeats forever. That was even faster. Okay, so, I mean, I apologize if I'm being pedantic here, but the real numbers have no holes. 0.9 repeating is 1. So, with that in mind, we're looking for the smallest number with the property that that number is greater than or equal to every number in this set, which includes 1, 1/2, 1/3, 1/4, and so forth. So what is the smallest number which is greater than or equal to 1 and greater than or equal to 1/2 and greater than or equal to 1/3 and so on?
I don't believe that there is a supremum based off what we just did.
I think there is. That's, I mean, the set A, let me write A more explicitly. So the set A is, and my pen is dying, so it's 1, 1/2, 1/3, so it's getting smaller, right? So let's just think about upper bounds. Is 2 an upper bound for A?
Yes.
Is 1.5 an upper bound for A?
Yes.
Is 1 an upper bound for A?
No.
What's the definition of upper bound?
Greater than all elements in the set.
Greater than or equal to all elements in the set.
Oh boy.
Ha. So 1 is an upper bound of the set. Is it the least upper bound? Is there any upper bound smaller than 1?
No.
No, because if it were smaller than 1, it wouldn't upper bound 1. Okay, so 1 is an upper bound, 1 is the smallest upper bound. What is the supremum of A?
1.
Good, okay. It's worth working through some of these. You already said this, but what is the infimum of A?
0.
Good. We could prove that if you want. I'm not going to ask you to prove it, but the way you would prove this is all of these numbers are positive. All positive numbers are greater than 0. That means 0 is a lower bound because it's smaller than all of these numbers, simply because they're all positive. There cannot be any lower bound which is greater than 0, because any small positive number, I could go far enough out on this list, these get smaller and smaller and smaller and smaller, and eventually I would get below that number which I claimed was a lower bound. So it has to be 0. Good. Okay. What's different? What is Z? What is different about this second one? This set, maybe B.
Let me Google what the Z set is.
Oh, come on. This has to be cached.
Wait, I'm gonna guess before I Google it. Would this be the real number set?
No, real numbers is R.
Then...
Hint.
No, wait, rational?
Well, rationals is Q.
No. Oh my god.
Here's the trick. Z comes from the
Z is
Germans.
imaginary, right?
No, imaginary is complex numbers. That's C.
Oh my god.
Z is from the German Zahl, meaning number. So this is actually all the positive and negative integers. So this is, dot dot dot, -1, 0, 1, 2. It's all the positive and negative whole numbers.
So Z is the integer set. Okay.
Yeah. Okay, so what is this set then? What is the set B? How is it different from A, I should ask? A was 1, 1/2, 1/3, 1/4. Now n can be any integer, not just a positive integer. As long as it's not 0, of course.
I believe that in this scenario, the supremum of set B would be would be 1.
Good. Supremum of B is still 1. That was very cruel of me to laugh at you, but I'm probably going to extract that audio of supremum afterwards. Oh, good. Okay. Yeah, supremum is 1 for the same reason. This is upper bounded by 1. What's the infimum now?
I believe that the infimum would be -1.
Good. Okay. So you see what this set is doing. This is taking basically all of the numbers in A and all of the negatives of the numbers in A, right? Good. Okay. Yeah, I'm just going to do this one a little fast. So this set C, you have to solve a quadratic. So this is, let's see, negative B plus or minus square root of B squared is 1 minus 4. This is going to have imaginary roots, isn't it? 4AC. Yeah, okay. So this thing, x squared, this thing is always greater than 0. Aha. So I've written this in a silly way because, that's not true. Why am I? Maybe I shouldn't go as fast as I wanted to. Okay, well, let's find the roots of this guy, and we want to find the places where this quadratic is positive. So maybe I should go to a different slide for this. Fuck. So.
OxyClean there?
Oh, that was my advertisement.
Yeah, that's just Clorox.
Clorox bleach. Okay. So we want to find the set of all numbers where this expression is positive. This is going to be some upward-facing parabola. My pen turned black. This will be some upward-facing parabola. So the space of x's where it's positive is going to be everything outside of possibly a region between two roots. So we should see, are there roots in the reals where this thing equals 0? So where is it true that x squared plus x plus 1 equals 0? Well, we can use our favorite method. So the roots x plus minus, I like this subscript, should be -1 plus or minus square root of 1 minus this 4ac over 2, but that's interesting because these are only complex roots. So it seems that this parabola has no real roots, which I think means that the parabola lies entirely above the axis where y equals 0. So if that's true, if this parabola is always strictly positive, we have a simpler expression for the set C of all x where this thing is positive. What is that simpler way of writing this set?
X is greater than 0? Well, x such that x is greater than 0.
Well, I think so x greater than 0 is this side of the line, but I think we were arguing that it's also positive over here as well, right?
Right.
So we have
x such that the value of x is greater than 0.
Well, there's a simpler way to write that set.
I know.
Absolute value of x greater than 0 is true for all reals, right? So I think this should be all of R, right?
Oh boy.
This is a perplexing way to write the real numbers. Okay, so if this is the reals, does the set of real numbers have a supremum or infimum?
No.
Right, okay, so it's unbounded, so there's no upper bound and no lower bound. Okay, good. None of these were proofs. I'll ask you to do some proofs about these to make sure everything's clear, but thoughts on...
I love that title, by the way.
the sup dog. Yeah, I thought it's pretty relevant, pretty professional title to use. Okay, I know you want to leave in like 10-ish, 15-ish minutes, whatever, so, but other questions on Suprema or Infima that you have now that we've seen them again really quick?
I don't believe I have any questions. And I just realized if I get off the call at 10, that means I've 30 minutes to get my shower and do the daily challenges.
Oh shit, yeah, you probably want more time than that. Okay, we should probably